This is video 3 of 3 for chapter 13.1. Here we will introduce net ionic equations. Net ionic equations include only those compounds and ions that undergo a chemical change in a reaction, which is in an aqueous solution. There are essentially 3 steps to writing a net ionic equation. To write a net ionic equation, the first thing we need to do is convert the chemical equation that we're used to working with into an overall ionic equation. So we'll write down step 1. And as you might note from looking at an overall ionic equation, this new equation is going to involve ions, not simply the compounds. So this is where our dissociation equations come into play. All soluble ionic compounds in the overall ionic equation are shown as dissociated ions in solution. The precipitates that we found in the last video are shown as solids. So write those 2 notes down. All soluble, so we have to look at our solubility rules, ionic compounds. Note that they have to be ionic compounds. Sugar is not something we're going to deal with here, even though it is soluble. And the precipitates are shown as solids. And we don't break those down into the ions. So soluble ionic compounds we break down into ions, and we use the symbol AQ for aqueous after those, and we'll get to an example where we do that. Precipitates are shown as solids, so they get an S after the compound. So let's look at our equation from the previous video. We had cadmium nitrate, and ammonium sulfide. And when we reacted them using the solubility rules and changing the charges of the various ions to get the compounds, we found that ammonium nitrate was formed, and that was an aqueous solution. It was still soluble, so it's still forming those ions in solution. However, when cadmium and sulfur came together, they formed an insoluble compound, cadmium sulfide. So we put an S after that, because it's a solid. So this was the equation we wrote out in the last video. Now we're going to write the overall ionic equation so that we can eventually get to the net ionic equation for that. So remember, we used the solubility rules to find cadmium sulfate was a solid precipitate. For step 1, we break up each of the aqueous compounds into their ions, as we would in a dissociation equation. And then we use the coefficients to account for previous subscripts and coefficients. So what that means is anytime we see an AQ, we need to break it down into the ions first. So cadmium, we said in the last video that had a 2+ charge. And then nitrate, the polyatomic ion list has a -1. And now we're adding these ions together, because in solution they're not actually together in this compound, they're just floating throughout the water. Now the part about the subscripts and coefficients, this 2 outside the parenthesis I'll highlight that in yellow. That 2 tells me that I have 2 nitrate ions. So now I have to use a coefficient in front of nitrate to show that I have 2 nitrate ions. There was no subscript after cadmium, so I only have 1 cadmium ion. Added to that, I have my ammonium, which is NH4 with a positive 1 charge. And there's 2 of those shown by the subscript 2, so I put a 2 out front of that. And I have the sulfide ion, S2-. And we found the charge of sulfur by looking at the periodic table, and we saw that sulfur was in group 6, meaning it needed to gain 2 negative electrons. There's no subscript there, so we don't need a coefficient here. It's assumed to be 1. From there, we produce an aqueous solution of ammonium nitrate, so we have to break those ions up. So we have ammonium, which is a positive 1 charge. There's a coefficient of 2 beforehand, so I still have 2 of those ions. Added to that, I have nitrate, which is a -1 charge. Since it's a coefficient of 2, that 2 applies to both polyatomic ions, so I put a 2 in front of the nitrate. And added to that, I have a solid. Now the solids are precipitates, they're actual solids. They're not freely floating around as ions in solution, so we cannot break them into ions. Here we just bring cadmium sulfide down like so and keep the solid subscript. The rest of these should still have the aqueous subscript to show that they are dissolved as ions in water. Notice that the aqueous ammonium ion here, it appears on both sides of the equation. The same is true of the nitrate ion. They're both still aqueous on each side of the equation, they're the same ion on each side of the equation, and there's the same number of them. Since the state of the ions are the same, they're both aqueous on either side of the equation, it shows that they have not undergone any chemical change. They're still present in their original form as aqueous ions. We call such ions spectator ions. Essentially, you can think of it as they are like spectators. They just sit around and watch the reaction occur. They watch what is happening around them as a spectator would, and that's why they get the name spectator ions, because they just float around in solution and don't actually participate. So I'll write down spectator ions. That's one of our vocabulary words. And again, it's ions that do not take part in a chemical reaction. And they are found in solution. They don't separate from the solution. They're still dissolved in the solution, both before and after the reaction. Both sides of the equation. To convert an ionic equation like we have here into a net ionic equation, the spectator ions are canceled on both sides of the equation. Because they don't change, we don't need to look at them. It's kind of like canceling out like terms on either side of an algebraic equation that you would do in math class. So step 2 of our 3 steps is where we cancel out our spectator ions from both sides of the equation. So what that would look like is the ones I have highlighted that I identified as my spectator ions, I would just cross them out. I have to make sure I'm crossing the same thing out, the same amount out on both sides. So I cross out my nitrates and I cross out my ammoniums. And what I have left is my cadmium ion, the sulfide ion, and the cadmium sulfide at the end. So I still will have the same elements on the left hand and on the right hand side when I'm done. I won't have gotten rid of anything that I'm going to need for the final equation. And then finally, our last step, step 3, is to rewrite the equation without the spectator ions. And this is what we call the net ionic equation. So for our example above, we would have our cadmium ion, and it is aqueous, and our sulfide ion, also aqueous, and we would produce the solid precipitate cadmium sulfide. Now this net ionic equation we just came up with applies not only to the reaction between ammonium sulfide and cadmium nitrate, but it also applies to any reaction where cadmium sulfide, this guy right here, forms as the precipitate. Because anytime it forms the precipitate, the other ions are just spectator ions and don't actually interfere with the reaction. So every time you have cadmium sulfide as the precipitate, this is the net ionic equation you're going to end up with. This is the end of video 3 of chapter 13.1. We will work on examples of writing net ionic equations in class.